Hello, my name is Ekaterina Hromtsova, and today I would like to present you a paper entitled Federated Learning for Cybersecurity, SOC Collaboration for Malicious URL Detection. This is a joint work with Dr. Christian Hammerschmidt from Delft University of Technology and Sofiane Lagroix and Radu State from the University of Luxembourg. This paper takes part in the workshop on Networks Meets Intelligent Computations in ICDCS 2020 conference. Before going into the details of our paper, I would like to make a quick overview of the federated learning concept. So, federated learning is a collaborative learning where each customer or agent or worker is trying to learn a joint shared model without sharing their data. It works as follows. Each customer trains a model locally on their local data for one or several epochs. Once they finish training, they send the model to a central server. A central server aggregates the models across all the customers and distributes back an updated version of a model. Customers in turns initialize their models with the newly received weights and start training on their data again. This makes one round of federated training, or one global epoch. In this work, we are focusing on federated learning for cybersecurity. In our case, the customers are security operating centers, managed security service providers, and other small organizations. And their goal is to collaboratively learn a shared threat detection model without having to reveal any sensitive data or any confidential information. So the goal of this paper is to use federated learning in various settings to tackle a real-world task of URL classification. We designed our experiments to answer the following questions. How much performance is lost by distributing training instead of learning a single centralized model on the data from all the participants? How does the number of agents affect the training of a model? What happens if agents have very different data? And finally, would federated learning work in a real-world environment? Our first contribution is the dataset that we collected. It consists of more than 700,000 malicious and benign URLs. The overview of the datasets can be seen in the graphs below. Within malicious class, we can also distinguish four different categories: phishing URLs, defacement URLs, malware, and spam URLs. As you can see from this graph, there is an imbalance within malicious subclass, as more than half of the malicious data belong to malware. After collecting the URLs, we extracted 72 basic lexical features, and we work on these features later on. Both the dataset and the feature extraction code are publicly available in GitHub at this link. For federated learning setup, we chose a very simple fully connected neural network with two fully connected layers followed by ReLU activation functions and a dropout after the second fully connected layer with a probability 0.1. We used cross-entropy loss and stochastic gradient descent optimizer with a learning rate 0.01. Note that all the participants in our federated scenario have the same structure of the model. As an aggregation mechanism, we use the standard federated averaging. This means that a centralized server is aggregating the weights by averaging them across all the participants. We consider several different scenarios based on the data partitioning across agents in order to assess the capabilities and limitations of federated learning. We have three main sets of experiments. The identically distributed data, where the data is equally split between workers and the label distribution is preserved. This is an idealistic scenario that is never achievable in practice. However, we use it as a benchmark for federated learning. The second set of experiments is label-based split, where each worker has an exclusive possession of one of the attack types, while the benign data is divided equally amongst them. This is an extreme case for federated learning. And finally, the third scenario is size-based split. It is the most realistic one, where each agent draws the samples randomly from the main data set, and we allow overlaps in this scenario. Instead, we classify workers by the size of the data set that they possess into small, medium, and large workers. So let's start with the first sets of experiments of identically distributed data. Here you can see an example of this distribution. So on top we have a main data set, and this is how we divided among agents. So from this picture you can see that each agent has both spam, malware, defacement, phishing, and benign data. We performed two sets of experiments with few agents, where we want to see if federated learning is better than a centralized learning. So by centralized, I mean when all the available data is assembled by a centralized agent. The second set of experiments is with many agents, 50 agents in our case, and we would like to see if federated learning is better than local training. In other words, would the agent prefer to participate in federated training or rather learn on its own data only? So here are the results of for these two sets of experiments. The top two graphs represent the train and test accuracy for federated agents. In this case, each agent has a relatively large amount of data. As you can see in the second graph, federated learner achieves almost the same accuracy as the centralized learner, and it shows more stable accuracy. For the second experiment, with 50 agents, each agent has access to much smaller parts of the initial data set. So obviously, a centralized learner will perform significantly better than federated training. However, if we compare federated and local training, we see that they achieve the same results after 100 epochs. So it takes a bit longer for federated training to achieve the same results, but it is more stable and it does not overfit, while the local training starts overfitting after around 25 epochs. This is because of federated averaging that plays the role of label smoothing that proves to be efficient against overfitting. So all in all, federated learning does not harm the performance in an identically distributed scenario, but it does not provide much benefits neither. After studying the behavior of the system in the unrealistic case of independent and identically distributed data, we proceed to another extreme case by splitting the data set by the type of attack. In this experiment, we have 4 agents. Each agent has the access to only one attack type. So agent 1 only has phishing URLs, agent 2 defacement, agent 3 has access only to malware, and agent 4 to spam. So after training locally on their data, each agent will be able to detect their type of attack. In this set of experiments, our goal is to estimate how well their models generalize on the other types of attack they haven't seen, and would they benefit from collaborative learning or not. So we started by creating a test set that consists of 10% of each attack type and 10% of the benign data. Note that due to the class imbalance in malicious URLs, there will be much more malware samples in our test set than defacement, phishing, and spam. After separating a test set, we distribute the rest of the data set between agents and run federated learning for 40 global epochs with 1 epoch per round. And we compare the resulting test accuracy of federated training to the accuracy on the same test set achieved by each agent from training exclusively on their attack. The result of this training is shown in this figure. We notice that the performance varies a lot depending on the weight initialization of the model. That is why we perform 10 runs and we report a standard deviation over these 10 runs. Now obviously agent 4 with spam gives the worst performance, as most of the data it has belongs to the benign class and it has very few samples of spam URLs. And it's only agent 2 with malware that reaches similar performance to federated learning. This might be due to the class imbalance that we discussed earlier, because half of the malicious URLs belong to malware class in our test set. In order to restore this label balance within test set, we create a new test set by selecting 1,000 samples of each attack and 4,000 samples of benign class. This left figure represents the result on this balanced test set. Now, from this figure you can see that all the agents benefit from federated training, even the agent with malware. And finally, in order to estimate how well the agents generalize to the attacks they have never seen, each agent excludes the type of attack from the test set. So for agent 1 with defacement would only evaluate on malware, phishing, and spam, and agent 2 with malware would only evaluate on defacement, phishing, and spam, etc. This graph shows that the advantage of federated learning is even bigger, as the gap between federated and local training for all the agents becomes even larger. So even the agent with malware gains up to 8% in its test accuracy, while agent with spam gains up to 30% in test accuracy, which means that each agent becomes significantly better in detecting other attacks they have never seen if they train jointly and collaboratively. The final set of experiments reflects a more realistic scenario where all agents have access to various attacks but differ in the size of the dataset they possess. To create a realistic estimation of the agent size, we analyze the report that gives an average number of the security alerts received by real security operating centers in 2018. We created a Gaussian kernel density estimation over the distribution presented in this report, and we draw the size of the agents from this distribution. We create 30 agents. Each agent randomly selects training samples from the training set regardless of the label, And we allow the overlap of the training sets between the agents, which also reflects the real-world scenario, as most common URLs will be present in many different agents. Based on the size, agents are grouped into small, medium, and large, with small being smaller than 50,000, medium agents being between 50,000 and 100,000, and large agent being between 100,000 and 1,500,000. As expected, small agents benefit the most from collaborative learning, gaining up to 30% in their accuracy. This graphic to the right represents the 3 bars zoomed in, so it's the same thing. From the right graphic, we see that medium and large agents perform only slightly worse than federated learning, only by 0.5% worse. However, they are less stable than federated scenario. So allow me to summarize our contributions. In this paper, we examined how federated learning can help problems with data sharing in cybersecurity, in particular in malicious URL detection. We collected an extensive URL dataset and extracted features from URLs. Both the dataset and the script for extracting features is publicly available. We proposed a federated learning-based approach for malicious URL detection in a managed security service provider setting. We modeled several scenarios taking into consideration the characteristics of the data, such as class balance and class distribution, together with the various sizes of customer infrastructure. We showed that small providers can achieve up to 30% performance improvement when trained in collaboration, while the big providers become more stable and generalize better with no cost compared to a locally trained model. Moreover, we found that smaller participants benefit from larger participants, obviously. Participants seeing different types of malicious traffic can generalize better to unseen types of attacks, increasing performance by 8% to 15% on average, and up to 27% in the extreme case. Participating in federated training never harms the performance of the locally trained model. And finally, in our experiment modeling a security as a service setting, federated learning increased detection up to 30% for some participants in the scheme. Thank you for your attention, and do not hesitate to contact me if you have any questions regarding the paper. I'll always be very happy to discuss it with you. Thank you again.